Hello and welcome to Don Labs. In this episode we're going to be talking about Kirchoffs laws. Kirchoff's first law is the current going into any node is equal to the current flowing out of it, and Kirchoff's second law is the sum of all voltage in a closed circuit must be equal to zero. Now we're going to use these laws in conjunction with Ohm's law and all of the stuff that we've learnt so far in our basic components playlist. So we're going to be using the theory on parallel and series circuits. As you can see, this basic circuit we have laid out here has a series resistor going into a parallel resistor network, and we're going to use Kirchoff's laws and Ohm's law to figure out some more values for our circuit. Now going to the first law, we have a node here, we have a node here, and what this law means is the current flowing through this component here will be the same here as it is here. It will be the same here as it is coming out of here. And this makes sense if you remember your theory about series circuits. The current in a series circuit is the same around the whole circuit. Now the second law, we have a potential difference of 9 volts up here. If we was to work out the voltage drop across this component and add it to the voltage drop across this one, and this one, the voltage of all of these components subtracted off our original voltage will equal 0. This coincides with the law of conservation of energy, because what goes in basically must come out. So what we're going to do is we're going to break this circuit down into smaller parts so that you can figure out which areas you can apply Ohm's law and with what numbers you need to use. Using Kirchoff's law, we know the current going in here is equal to the current going out here, so we can count this whole block as a single resistance in series with this resistance here, because we know the current going into this resistor is the same as the current coming out, and if the current coming out of here and into here is the same as here, then this whole circuit is a series circuit with these block of resistors as a single resistance. We know the formula for a parallel network, and the total resistance in a parallel network is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So we can look at our parallel network here. 1 over RT is equal to 1 over 220 plus 1 over 220 plus 1 over 470. And when we rearrange this, we get a total resistance in this parallel network of 89.1 ohms. Now we can add this 89.1 ohms to our 470 ohms for R4, which is how we work out the total resistance in a series circuit, and we can use this total resistance to find out the current in the circuit. Now, using the triangle, like I explained in my video on Ohm's law, just to make it easier for you to remember how to rearrange your three variables, voltage, current and resistance, we know that current is equal to voltage over resistance. So our current in the circuit is our 9 volts over 470 ohms plus 89.1 ohms. That gives us a current of 0.016 amps or 16 milliamps. Now that we have our current, we can work out the voltage dropped over our first component in this circuit, which is R4. So voltage is equal to current times resistance. So 16 milliamps multiplied by 470 ohms gives us a voltage of 7.57 volts. So now for R4 we have all our three variables of Ohm's law, which is current, voltage, resistance. Referring back to Kirchoff's law, the second law states the sum of all voltages in a closed circuit must be equal to 0. So if we are counting this parallel network as one block, and we know from our theory that voltages in parallel are all equal, and we have this voltage here, and we know that our original voltage minus all of the voltages in our circuit must equal 0. Therefore, this voltage minus this voltage must equal this voltage of this block, and because we know that in parallel all voltages are the same, it will be the voltage dropped on each component. So our original potential of 9 volts minus our 7.57 volts, which we worked out for R4, gives us a remainder of 1.43 volts. So we have dropped 1.43 volts across this component, R1, the same across R2, and the same across R3. Now we have two variables of R3 for components R1, R2 and R3, which means we can then find the current across each component. Current is voltage over resistance. So for R1 we have our 1.43 volts, the voltage dropped across the component, divided by 220 ohms gives us 6.5 milliamps. In this case, R2 has the same value as R1, which also gives us the same answer of 6.5 milliamps. Referring back to Kirchoff's law again, the current going into any node is equal to the current flowing out. We know the current going into this node here is 16 milliamps, the same as the current for the entire circuit. We have already just worked out we have 6.5 milliamps here and 6.5 milliamps here. Added together, that gives us 13 milliamps. We know the current has to equal 16 by the time it comes out here, therefore R3 has to be 3 milliamps. So we've worked out the current at R3 by only applying Ohm's law to the other part of the circuit. We can then go back and work this out just to confirm this is true, and if you take our 1.43 volts and divide it by 470 ohms, you will get 3 milliamps. But understanding that Kirchoff's law states the current going in must equal the current coming out just makes it a lot easier for us to know where to apply each value. Now we can take this one step further and use the power triangle to work out the power dissipated across each component. Power equals current times voltage. And if we go to R4, we have our current, we have our voltage, multiply them together and we get 0.12 watts or 120 milliwatts. That's how much heat will be dissipated across this component. So as I've said before in previous videos, it's very important to not only work out your three variables in your Ohm's law, but also work out the heat dissipated across the component, just to make sure the component is up to the job. We can do the same again for R1, R2 and R3 because we have the voltage, we have the current and we have the resistances. So R1 is 6.5 milliamps at 1.43 volts. We're going to get 9.3 milliwatts. Same for R2 and R3, we get 4.29 milliwatts. So now we're going to go to the breadboard and we're going to check the theory with the multimeter to make sure we're getting the same results. So up here we just have our power supply coming into the board. We have our positive here, the same as in our circuit diagram, going into our first series resistor, which is 470 ohms through the resistor. And then that's linked into this parallel network here, which we worked out as 89.1 ohms. And then that's coming to the ground to complete our circuit. So I've set my multimeter to 20 volts. First of all, I'm going to measure the input. So we have our 9 volts input. Across the first resistor, 7.52, 7.51, and across our parallel network 1.43. So that is a simple demonstration of how you can apply Kirchoff's law in conjunction with Ohm's law and all of the other skills that you've learned in the basic component series. Doesn't matter how complicated the circuit is, you can always break it down into individual parts, and that is how you apply all of the skills we've learned so far in the basic component series. Thanks for watching, don't forget to like and subscribe, new series coming out soon, and don't blow up.